All right, welcome to chapter 12. We're going to knock out both sections A and B today. We're going to go through all three of Newton's laws of motion. So lots of information today, okay? But to talk about his laws of motion, we need to talk about forces first. And no, not that kind of force. May the force be with you. A force in science is any push or pull. You need a force to make an object move, okay? Again, not like Yoda, even though he could lift up the ship without, applying a force to it. That's different. If I need to move anything, I have to actually apply a force to it. And we measure force in newtons, and we use the abbreviation capital N for that. Okay. So now we're talking about dynamics. Last chapter was kinematics. Now we're into dynamics because we're going to study those forces that cause the motion, okay, and how they change an object's motion. We have contact forces, which only act when the objects touch. So if I get, I don't know, hit with a dodgeball, okay, that would be considered a contact force because the ball actually made contact with me. That force would be applied to me, okay? If I get hit by a car, obviously there's going to be a big reaction to that, also a contact force. But there are also field forces which can have an effect on an object without actually touching, okay? Gravity acts on us even if we're not touching the surface of the earth, okay? That's what makes us fall. Magnetism, when magnets get close enough together, they'll just come together. And electricity can actually act over a certain field as well without having contact, okay? So those are field forces. All right, let's talk about balanced versus unbalanced forces. Basically, if a force is balanced, there's not going to be movement. The net force is zero. They cancel each other out. So if you look at this top scenario here with our tug of war, we've got this group pulling in this direction with a force of 300 newtons, that group pulling in the opposite direction with the same amount of force. That rope's not going anywhere. It's perfectly balanced, okay? You have something hanging here and it's not going to be moving. The net force is the sum of all the forces, okay? Well, if one team starts pulling more, so now our arrow is a little bit bigger, okay? They are actually pulling with a force of 400 newtons. This team is still only pulling with 300 newtons. So now we have a net force of 100 newtons in this direction. That's now an unbalanced force, which means the rope is going to move in that direction, okay? If that team really got going and they were pulling with 500 newtons, we would have an unbalanced force and a net force of 200 newtons in that direction, okay? And so we use these arrows to kind of do some math with, all right? So arrows come up a lot, and we've got these force diagrams that kind of show what's happening. They show the direction of the force and so on. So it shows that an object and a force is acting as a vector because there's a direction. The direction of the arrow is very important to this. And so these are vector measurements, okay? Again, the force is drawn as arrows. This diagram in particular doesn't show it as clearly, but oftentimes the magnitude is represented by the size of the arrow. You can see, so this is a 10 Newton arrow versus a 5 Newton arrow. The 10 Newton arrow is a little bit longer. I like the diagrams that make the arrows fatter too, because it's just easier to see visually. And then the direction of the arrow shows the direction of the force, okay? So these are going in opposite directions, but they're going towards each other now, okay? If the forces are in the same direction, like these, they're going to be given the same sign. This diagram gives you color, so they're both red. We could think of those as both negative. Doesn't matter, okay? If in the opposite direction, they're given different signs, okay? I'm going to say this is positive 10, and I'm going to say this is negative 5, okay? So we're always going to add these up to figure out what the net force is. Okay, so negative 5 plus positive 10 gives us a positive 5 net force in that direction. The direction is vital, okay? And that should make sense. That black arrow was pushing with twice as much force as that red arrow was. And so the black one is just going to be stronger, okay? Move down to the second situation and the exact opposite is true. Now it's just going a different way. So the stronger force is moving that way. So there'll be an overall net movement, net force of 5 newtons that way. If they're going the same direction, we just add them up. What's 5 plus 5? It's 10. And so these will kind of stack up on each other and you get a larger force as a result, okay? Let's see if we go back here. You can see that those arrows are showing the same information, okay? They show the direction of the force, and the size does change. The 400 Newton one was a little bit longer, okay? Go to this again. All right. It's time for Newton's first law of motion. But before I do his first law, you need to know what inertia is, okay? So basically, objects resist change. They don't like to change. And so the tendency for matter to resist change is known as inertia, okay? Now, because of that, we get Newton's first law. And it's stated as this: an object at rest will stay at rest, and an object in motion will stay in motion, unless they are acted upon by an outside unbalanced force, okay? So I have a baseball, okay? You know this. If I throw that baseball, it's not going to go on forever, okay? Because gravity and friction, air resistance, are going to act on this baseball. But if I could remove all that, if I could go into outer space and I could throw this baseball, once it's in motion, it's going to stay in motion until something acts upon it, okay? An object at rest is going to stay at rest. It's not going to magically start moving unless a force gets applied to it. Somebody kicks it, somebody picks it up, something like that. And so objects don't just move on their own, but they don't stop on their own either, okay? And that's Newton's first law. The biggest outside forces that we deal with here on Earth are air resistance and gravity, okay? Air resistance causes friction to stop things. All right, let's jump into Newton's second law of motion. This relates acceleration of an object. So the acceleration of an object is directly proportional to the force acting on the object, and it is inversely proportional to its mass. This has to do with the math of things, okay? So it's also known as the law of acceleration, okay? Here's the formula. Force equals mass times acceleration. F is force, m is mass, a is acceleration, okay? So let's go back to the proportional, okay? The acceleration and the force are proportionally related to each other, meaning if one goes up, the other one also goes up. The mass is inversely proportional to that, but it's easier to think of that in this form. If we rearrange the formula and look at the equation this way, this is actually how Newton wanted the equation to be written in terms of acceleration. So what that means, that directly proportional means if the force gets bigger, so does the acceleration. That should make sense. The more force I put on this object, the faster it's going to go, okay? But the mass is inversely proportional to the acceleration, which means the bigger the mass, the slower the acceleration. That should also make sense. Heavier things are going to go slower because they require that much more force to move them, okay? This form of the equation also shows us why there is no motion without force. If I put 0 in here for force, then acceleration is 0. The object is not going to move, okay? All right, third law of motion, cruising along, okay? This one is simply stated for every action, there's an equal and opposite reaction, okay? It's also known as the action-reaction principle. And this is how rockets work. That's my SpaceX rocket that I got to see a little while ago. What's happening is the rocket is shooting all kinds of fuel in a downward direction, okay? And as it pushes on the ground pushes up with an equal and opposite force. And this is what allows the rocket to take off, okay? As the fuel continues to push out, it's also pushing up on the rocket in that opposite direction, okay? You can also have this equal and opposite reaction without movement, though. On page 280, the book talks about like a rock climber just hanging from a rock. Okay, the rock climber is pulling down on the rope, but the rope is pulling up with an equal, balanced, opposite force. Okay, so there's no actual movement, but it's still considered an example of this third law of motion. Pulling on that rope or chain or whatever it is an example of tension. Okay, it's a pulling force, and if you're pulling down, whatever the rope is attached to is pulling up in the opposite direction. Okay, we have lots of examples of this. Okay, if you've ever been ice skating and you try to push somebody away from you, you actually go backwards in the opposite direction. So the force you apply on somebody acts on you in an equal and opposite direction. A gun, this is why a gun has recoil. It shoots out a really large force in that direction with a projectile, but that's felt as a recoil of the gun. It's felt in the opposite direction. You have to be careful stepping out of a boat. When you step, you push. And if you push the boat too much, it might slip out from under you. And there's all kinds of fail videos to show people doing this. Okay. This one's a little weird. You can see a diagram of this on page 281. Normal is another word for something that is perpendicular to the surface. Okay, so if that little yellow line is the surface, that arrow would be perpendicular to it, and that would be called normal in science. Excuse me. So normal force is a return force that is perpendicular to the surface. So if I'm standing on the ground, okay, there's my legs. If I'm standing on the ground, I'm applying a force straight down. But the ground is actually applying a force back up on me. Okay, those are equal and opposite reactions. Since those forces are perpendicular to the surface, those are considered normal forces. That's all. Okay. You guys are going to do this pretty soon with rockets. Okay. All right. That's it.